All the incredible AI we're seeing today, everything from ChatGPT to Gemini and all the amazing tools in between? Well, what if I told you that almost all of it can be traced back to a single research paper from 2017? It didn't make a huge splash at the time, but it quietly gave the world a brand new blueprint for building artificial intelligence. So, let's dive into the paper that really, truly changed everything. Attention is all you need.
To get a sense of just how massive its impact was, just look at this number. This paper has been cited in other research over 200,000 times. I mean, it's on track to be one of the most influential scientific papers ever. This wasn't just a small step forward. It was a foundational shift for the entire field. So, what was the big problem they were trying to solve that led to such a revolution?
Okay, so before 2017, AI had a major problem, especially when it came to understanding language. The main models at the time, things like recurrent neural networks or RNNs, were built to work kind of like us. They read one word at a time in order, and that, it turns out, creates a huge bottleneck.
I want you to imagine trying to read a whole novel, but you're looking at it through a tiny straw, seeing only one word at a time. By the time you get to the final chapter, you've probably forgotten some key details from the beginning, right? Well, that's exactly the challenge AI was facing. For a model to understand that the word "it" at the end of a paragraph refers to a specific character mentioned pages ago, that was incredibly difficult and often just failed. This was the core problem of long-range dependencies, and it was holding everything back.
This chart just lays out the difference so perfectly. On the left, you've got the old way, the recurrent networks. Information had to travel down this long sequential path, and the further it went, the more the original context would just fade away. It's a problem they called vanishing gradients. But then look at the transformer on the right. It completely changes the game. It processes everything all at once, in parallel, creating direct, instant connections between any two words, no matter how far apart they are. This was the breakthrough.
So how did the researchers at Google Brain manage to break through this sequential wall? Well, they came up with a really radical idea. They thought, what if we just got rid of the step-by-step process altogether? Instead of reading word by word, what if a model could look at every single word in a text at the same time and figure out for itself how important each word is to every other word? This is the beautiful core idea of self-attention.
Self-attention is the engine that makes the transformer go. For every single word it looks at, it calculates a relevance score, an attention score, with every other word in the text. So in a sentence like, "The robot picked up the ball because it was heavy," self-attention is what allows the model to connect it directly to ball and understand it's not talking about the robot. It's building this dynamic map of relationships across the entire input all at once.
And here it is, the mathematical heart of attention. Now I know this formula can look a little scary, but the idea behind it is actually incredibly intuitive. Just think of it like a tiny, super efficient search engine. The query, or Q, is the word the model is trying to understand right now. The keys, or K, are all the other words in the sentence. They're like the index of topics it can search through. And the values, or V, are the actual information contained in those words. The formula just helps the model compare the query to all the keys, find the most relevant ones, and then pull in their values to give the original word its full, rich, contextual meaning. It's brilliant.
So with this incredibly powerful new self-attention tool, the team built an entirely new architecture around it. It was clean, it was powerful, and most importantly, it was built for parallel processing. That meant it could be trained on massive, massive data sets using modern hardware way more efficiently than anything that came before. Let's take a look under the hood. This is the iconic diagram from the original paper. It might look a little complicated, but it basically boils down to two main parts. On the left side, you have the encoder. Its only job is to read the input, let's say a sentence in English, and build a deep numerical understanding of it. Then on the right side, you have the decoder. It takes that rich understanding and uses it to generate an output, like translating that sentence into German, one word at a time.
Now, this architecture had a few other strokes of genius. First, multi-head attention. Instead of calculating attention just once, it does it many times in parallel. You can kind of think of it like looking at a sentence through 8 different colored glasses at the same time. One head might focus on grammar, while another looks at who's doing what. Then there are positional encodings. Since the model sees everything at once, it doesn't naturally know if a word is at the beginning or the end, so they basically gave each word a little mathematical GPS signal to tell the model its position. And finally, the really big one, no more recurrence. Getting rid of that one word at a time loop is what finally opened the floodgates for the massive parallel training that defines AI today.
So you see, this wasn't just a slightly better way of doing things, it was a completely new recipe that could be scaled up to an unbelievable degree. By unleashing this power of parallel computing, the Transformer kicks off a literal explosion in AI capability, what you could call the AI Big Bang that led us right where we are today.
This timeline just says it all, doesn't it? The paper drops in 2017. Just 1 year later, Google's BERT model comes out and just shatters all the existing benchmarks for understanding language. Fast forward to 2020, OpenAI releases GPT-3, and the world gets its first real glimpse of what these large-scale generative models can do. And of course, that led directly to ChatGPT, which put this incredible power into the hands of millions. It's a straight line, all starting from that one paper.
And the craziest part? The impact went way beyond just text and language. As this quote explains, the Transformer became the new gold standard. Because the architecture is so flexible, researchers quickly figured out how to apply it to other things. We now have vision transformers for image recognition, it's used for audio processing, and its ideas are even being used to tackle huge scientific challenges in biology and chemistry. It's just an incredibly versatile and powerful idea.
So when you really step back, attention is all you need did so much more than just give us a new model. It gave us a whole new way of thinking about how information is processed. It was a fundamental shift away from slow, sequential logic to a parallel, holistic approach that's all about understanding the web of relationships between things. It's a new way of thinking about how meaning is created.
The Transformer architecture, through this mechanism of self-attention, essentially gave AI a powerful, scalable, long-term memory. But here's the thing. Memory isn't the same as understanding. It's not the same as reasoning, or creativity, or consciousness. The breakthroughs we've seen are absolutely mind-blowing, but they also bring us to this next massive question. We've solved the problem of attention. What's the next great bottleneck that we need to break through?